Hey guys, welcome back to a new video. So today we are going to build neural networks from scratch. So when I'm building these neural networks, I'm not going to use neither TensorFlow nor Keras, not even PyTorch or any of those deep learning libraries. I'm simply going to use the most basic Python built-in functions, and I'm also going to use math library. Okay, so why should we even learn neural networks from scratch when we already have TensorFlow? I've seen so many experienced programmers and data scientists who don't even know how backpropagation works. Okay, so there are fundamentally two aspects when it comes to neural networks: forward propagation and backward propagation. Once you understand both of these, you can clearly understand how exactly is each layer built, what is happening inside of those layers. So, what are the different types of activation functions? Why do you even need all those activation functions? You Once you master all of these, you can go ahead and create your own model architectures. Once you understand what exactly is happening inside of each layer, you'll be easily able to put together all different pieces and create wonders. That's basically how we came up with unit architecture or GPT model or any other complicated model that we're going to face in the near future. So fundamentally, there are two aspects: forward propagation and backward propagation. Let's go ahead and understand what exactly these are. So when it comes to forward propagation, we have just the types of layers. Okay, how these layers are going to interact with each other. Now in a neural network, if you take any simple neural network, we have input layer, hidden layers, output layer. So on the diagram here you can see the yellow bubbles are input layer and all the green bubbles are hidden layers, and the output layer is going to be the red one. So depending upon the use case, depending upon the type of problem that you're trying to solve, whatever your model's final goal is, you're going to decide the output layer. So for example, if you're doing a regression problem, you'll have only one bubble in the output layer. So whenever you let's take a simple example. Let's say you want to predict how many students are going to enroll in this particular semester. Now you can take entire historic data and you can train your model, and when you send in all the parameters of present semester, the final output layer, that red bubble, is going to give you a number. This number is going to be the prediction of your model. So your model is predicting that, hey, you are going to receive these many number of students in the upcoming semester, right? And if you have a binary classification problem, you will have two bubbles, first bubble and second bubble. So the first bubble belongs to class A, second bubble belongs to class B. Now let's say you are classifying dog versus cat problem. Okay, so you have bunch of images and you want to check, or you want your model to predict whether a particular image contains image of a dog or image of a cat. So you'll take all of your annotated data, labeled data, you'll send that to your model and it will learn and analyze all the patterns, and now you'll give completely brand new photograph. From this image, your model is going to give you two outputs, two bubbles, two outputs. So if the first bubble, let's say the first bubble's output is 0.94, second bubble output is going to be 0.06. So which means my model is 94% confident that the image belongs to class A. If class A is dog, then the image is of a dog. If class B is of cat, then the image is of cat, right? So which means probability of that image having a dog is 0.94, 94% probability. And that's how you design the output layer. Based on your use case, you'll add or remove your number of perceptrons in the output layer. So the second thing is going to be backpropagation. So what is backpropagation? Backpropagation involves two fundamental mathematical concepts: derivatives and chain rules. So what are derivatives? Let's say you have a function and you will send x as an input to this function, and you will receive y as the output. If you want to calculate what is the impact of x on this output, dy by dx is the formula. So let's go ahead and use Python code to understand these derivatives, and for now let's ignore the chain rule. I'll get back to chain rule. I'll explain what exactly is chain rule, how do we implement it in neural networks when we get there. So let's get started. Let me open my Jupyter notebook and we can start building our neural networks. Okay, now I'm going to create a simple function f of x, and I'll do some simple calculations here. So let's go with x square, or actually just go with 2x plus 8x minus x. So it's a very simple calculation, and for this function I'm going to pass 3. So when I send 3, I got 27. Now what I'm going to do is I'll take f of 4. So I got 36 here. So if you assume that whatever my function is returning is y, and whatever input I'm sending in as x, then dy by dx is a derivative. Okay, so what do I mean by this? Well, this means dy by dx is going to indicate how does x affect my y. Okay, so that is basically how we represent in numeric form. Okay, so when you write this exact sentence in mathematical form, we get dy by dx. Okay, I'm going to comment all of this, and in a new cell I'm going to create one more function. So this is going to take a few more inputs, let's say a, b, c. Now for this a, b, c, let's do the same operation actually. This is going to be a, this is going to be b, and this will be c. Okay, there you go. Now let me initiate a as 3.0, b as 4.0, c as 5.0, and let's call this function. Okay, so when I run both the cells, I got 33 here. Now I'm going to create one more variable here called h. So h is going to be 0.1. So for this function, if I modify my a by h, then the output changes from 33 to 33.2. Okay, now so now we have 3 variables and one h. So with the help of h, we can calculate dy by dA, dy by dB, dy by dB, dy by dC. Okay, so how do we calculate this? Now what does this indicate? Dy by dA, this tells us how is my a affecting y. What is the effect of a on y? So which means if I modify my A by a small amount, what is going to happen to the output? How will my Y change? Right? So to calculate this, we have a formula. Let me go to Wikipedia. So the formula is called as a derivative formula, and if I go to Wikipedia, there you go, this is the formula. So f is the function, a is the input. So if I want to identify the effect of a on my output, then for the same function I can send a and I can add some small amount of bias called h, and if I do this calculation properly, then I'll be able to identify what is the value of dy by dA. So let's write the same formula, a comma b comma c, everything is going to be the same. Let's divide everything by h. Here I've got the value as 2.0. So dy by dA is 2. Let me write the whole thing down. Okay. Similarly, if I modify my b value, then the output is going to change by this amount. Similarly, if I modify my c value, then my output is going to be reduced by this much. So using this formula, we can calculate these the dy by dA values, dy by dB value. So with this formula, we can easily calculate how exactly. So with this formula, we can easily calculate by how much is each independent variable affecting the output. This is going to be very useful in backpropagation, because in the neural network, I closed it. Okay. If I go back to the neural networks diagram, so in this neural network, we have all these hidden layers, and each hidden layer has neurons. These are all the green bubbles. So all the green bubbles are neurons. So in backpropagation, we want to understand how exactly is each neuron affecting the output. Okay, so if you assume all of these as x, let's assume this one green bubble as x and this red bubble as y, and if you want to understand how this green bubble is affecting the output, then we can calculate dy by dx. Okay, so that is essentially what we are going to do in the future. Now I hope I've clearly explained you what exactly derivatives are. Now let's go ahead and start building the neural network. Let me create a class called neuron. So this is going to be this neuron right here. Okay, so the technical term for all of these neurons is perceptron. So if you look at a perceptron, we've got a bunch of x's, bunch of w's, and one summation, and one more bubble called step function, and then we have an output. So what is happening here is, this is a perceptron. If I go inside of a perceptron, I'll find neurons. Okay, so every single element that you see here, all of them, they're all neurons. Now let's go ahead and understand what exactly are neurons. So for that, let's create a neuron. So this will contain an init class and whenever I'm creating a neuron, I need to pass some weight to this. So this is going to be a property. Okay, so that is defined. Now let's go ahead and run this, and I'll create a neuron 3.0. Now when I try to print it, obviously I'm going to get the address of that object. I'll say a dot weight. Now when I run this, okay, there you go. So the neuron has been created along with a weight, but I don't want to get the weight. I want to get, whenever I call the function, I want to get the weight of that function represented in a string value directly. So I'm going to use one more built-in function called repr. So here I will be returning weight is equal to self.weight, and this is going to be an f string. Now what happens is, when I run it, I'll directly get the value of a string value. This is going to say weight is equal to 3.0. okay, so far good. Now if I go back, so all these neurons, they should be able to communicate with each other. So when I say communication, we should be able to perform basic arithmetics, plus, minus, multiplication, division. Okay, so let's go ahead and create one more neuron called b is equal to neuron of 4.0, and let's do a plus b. This is going to throw us an error because neuron is an object that we have created, and Python doesn't know what exactly are the rules and regulations to add neuron objects. So to define those rules, we can basically use the add function. So for the add function, I'll pass one variable and I'll return self.weight plus other.weight. So essentially what I'm doing here is, for example, if I have a is equal to 1, b is equal to 2, whenever I do a plus b, this is an equivalent of a dot add a dot add of b. So the add method is going to take care of the add symbol. Okay, there you go, the answer is 3. So that is how add works. Now we are going to implement add here. So I'll take other, and I'll take other dot weight, and I'll take self dot weight. I'll add them up. Let's run this. Let's run this, and we got 7.0. But notice here, this is a float value. Since we are returning a float value, we want to return a neuron. So what I'll do is, before returning, I'll simply convert this into a neuron. There you go. Now this is a neuron. So that was the add function. Similarly, we need functions for subtraction, multiplication and division. Division, multiplication, subtraction. There you go, all of them are working. Now my neurons are able to communicate with each other, but if I do 3 plus a, or actually let's do a plus 3. So int object has no attribute weight, because when I do a plus 3, this is essentially going to become as a dot add 3. 3 is a float data type. Now 3 doesn't have any particular weight to it. So what we are going to do is, if I'm passing any other data type which is not a neuron, I'll convert that into a neuron and then do the addition. And I'll repeat this for all operations. There you go, this is working. Now similarly, if I do 3.0 plus a, this should also work, right? No, it doesn't, because I know how to add an integer to my neuron, but Python doesn't know how to add a neuron to an integer. So Python can't understand what exactly it is supposed to do when I do this. Okay, so for this problem, what we can do is, we have a method called radd, so R stands for reverse, so this is basically reverse addition. So we will return self plus other. Let me remove this, and when I run this, there you go, it is working. Okay, so now that my neurons are able to communicate with each other, we can go ahead and calculate the derivatives. Okay, but before we go to the derivatives, we are going to use GraphViz library to visualize how these neurons are communicating with each other. Okay, so let's take the same equation. Let me paste it here. And here I'm going to create one more neuron called C is equal to neuron of 5.0. Now if I run this, oh actually we have added it for addition. Let's go ahead and do the same thing for multiplication. Okay, there you go. So we got a result here, but we are going to break this down into multiple steps. So let's see how that looks like on a graph. Okay, so before we go there, I want to do some small modifications to this class. So I'll be adding all of these parameters here. So what are they? Well, first one is label. Label is going to be label by default I want label to be blank. So what is label? Label is going to be the name of my neuron. Okay, so for this neuron I want this to be named as capital A. Okay, that is going to be the label. And what is the gradient? For now let's put the gradient as 0. And what is parent? Okay, now let's say we have A plus B. Okay, so we are adding two neurons, and when you add both of these neurons we get C as the output. C is the child, A and B are parents. And what did I do here? What is the operation that I've done here? It is plus. Okay, so I'll store the parents here, and I'll store the operation here. So parents and operation. By default parents is going to be an empty list, and operation is going to be an empty string. Okay, so which means whenever I'm creating a new neuron from scratch, I don't have to worry about passing label parents operation. I just have to give a weight, that's it. And wherever I want, whenever I want, I can pass label just for the purpose of visualization. Okay, now let's modify this a little bit. So E is equal to A times 2, and F is equal to this part, G is going to be E plus F, and I'll store G minus C in H. Let me just make this easy to understand. Okay, there you go. Now when I run everything, we've got ABC neurons, and all of these calculations are being done here to give us H. Okay, cool. Okay, cool. Now similarly I'm going to pass labels for all these neurons. This is going to be B, this is C, okay, let me paste this cell here. So this is the draw dot function. We also have trace function. I'm using that trace function instead of the draw dot. You can see it right here. Okay, so the draw dot function is utilizing the GraphViz library to visualize all of these neurons. Let me run this, and actually I'll take this entire cell and I'll throw this at the very top. Okay, so we don't want to get interrupted by this function. It's a pretty long function. Okay, now we are back here. Now I'm going to use draw dot of h. Okay, we get this. Cool. So we are able to see h, but now we want to look at the parents of h. Okay, so which means what is h? H is the resultant of this subtraction, and g is the resultant of this addition, f is the resultant of this multiplication, and all these sort of operations, right? So whenever I'm doing any of these arithmetic operations, I'm going to pass all of these parameters. Actually, not the label, but both of these parameters. Self and other are being added, right? And the operations are plus, minus, multiplication and division. Okay, let's run this and run this. Now when I visualize, there you go, I see a neat graph over here. So if you look at the comparison, the first thing that we are doing is multiplying a with 2, and we are multiplying a with 2, similarly b with 8, and these are giving us f and e. Now when I combine f and e, I get g. When I combine g and c, and I do a subtraction to get h. Okay, I think I might have given small c here. Let's capitalize this, and there. Let's visualize all of this once again. There you go. Oh, the order has changed, so c has come to the top and g has gone to the bottom. This happens a lot with Graphers library, no big worries in this. Okay, now we are able to easily visualize all of these things. So what is gradient? H is the final output and f is the intermediate output, right? Now when I calculate dh by df, okay, so when I calculate how is f affecting my h, how is f affecting my final output, then I can represent that with dh by df. Okay, this value is going to become gradient of f. Okay, so we are going to store this value instead of the grad. Okay, so now we need to calculate all of these gradients. Okay, right now everything is 0.0. So to calculate all these gradients, first we need to start with the very last node. Okay, so the very last neuron here is h, and whenever you're dealing with back propagation or any equation, you're calculating dh by dh, and the value of this is always going to be 1. So whenever you derivate a variable with itself, the value is going to be 1. Actually, let's go ahead and quickly take a look at derivative formulas. Okay, I think these are very much helpful. So the first three formulas, these are the most basic derivative formulas, and we are going to use them in the back propagation. Okay, so when you have k as constant, whenever you're derivating a constant value with a variable, answer is going to be 0. Whenever you are derivating a variable with itself, answer is going to be 1, just like how we have seen just now. Now whenever you have k as a coefficient of this variable, k will come out, dx by dx is going to be 1, so the remaining answer will be k. We are going to apply this third rule for c and g. dh is equal to 1. Let's take this, let's put it here. Actually, let's go ahead and add a code block, and here I'll say dh by dh is equal to 1. Now what do we need to calculate? We need to calculate the gradient of c and g. Okay, c and g. So this is going to be dg dc, and we are calculating these with respect to dh. So dh by dc, dh by dg. We need to calculate this part. So when I'm calculating dh by dc, I know what is h. Okay, h is equal to c minus g. Actually, I think it's better if we use a different equation here. So I'm going to do some modifications to all of these calculations. Okay, so these are completely new calculations here. So I'm taking a and b and multiplying them to get d. C and d are being added to give me e and f are being multiplied to give me g. So this is going to become dg by dg. So that will be 1, and dg with respect to e. This is what we need to find out. And dg with respect to f. We need to find out both of these. So what is g? G is equal to e times f. I know this, so I can say e times f divided by d e. Now if I take f outside, we got df by df. Answer to this is going to be e multiplied by 1.0, which is e. What is the value of e here? 0.46. Oh, I'm sorry, this is supposed to be e, so that means my e will stay here, f will come out. Okay, there you go. So what is the value of f? It is 2.0. So dg by de is going to be 2.0. So if you observe what is happening here, actually let's go ahead and do this as well. So we already know that g value is e times f by d f. This time e is going to become my constant. E times 1. This value is going to be e. So dg by df is going to be 0.46. So if you observe what is happening here, if I remove all of this, then I can simply write this like this, and I'll take away all of this nonsense. Okay, I'll put it as multiplication. Right, since we're doing multiplication here, we got these as the gradients. Okay, cool. Now I'm going to write the same thing here. I know that g dot grad is equal to 1.0, e dot grad is equal to 2.0, f dot grad is equal to 0.46. Let me run this. Let's visualize all of this. There you go, the gradients are working perfectly. Now let's go one step back and find out the gradients of C and D. Let me move this a little bit here. Okay, we are going to calculate dg by dc, dg by dd. These are the values that we need to find out. Now remember guys, we are calculating the gradients with respect to the output, and that is the reason why I've written dg by dc, not de. We don't care about what is in the next level. We don't want to take any other neuron into consideration. We want to compare how this neuron is affecting the final output. This is the final output, g, dg by dc. Okay, we want to understand this particular value. To do this, we have chain rule. So this is where we are going to learn about chain rule. So what is chain rule? If I go and pull up the Wikipedia page of chain rule, okay, so if a variable z depends on the variable y, which itself depends on variable x, then z on x, so z depends on x as well, right? Pretty obvious. Now when that happens, if I want to calculate dz by dx, first I'll have to calculate dz by dy, and then I need to calculate dy by dx. Mathematically we are simply going to cancel dy and we will be left with dz by dx, but theoretically you can calculate the derivative of y with respect to z and x with respect to y, and when you multiply them you can easily understand this relation. Right now we got C, E and G. Right now C is affecting my E is affecting my G. Somehow if I can understand the amount of effect that C has on E, and if I can understand the amount of effect that E has on G, then I can put both of these numbers together and understand how C is affecting G directly. Okay, which is this part. Now from the chain rule we know that this can be written as dg by de multiplied by de by dc. Okay, we know dg by de, right? The value is 2.0. What is de by dc? Let's go ahead and understand this. I'll copy this, I'll paste it here. Now what is E? E is basically an addition of C and D. So I'll do C plus D, right? So when I split this entire thing, I can write this as dc by dc plus dc by dc, dc by dc plus dt by dc. D here is a constant value, right? Now whenever I do a derivative of a constant, just like how we have seen in the formula, dk by dx is going to be 0. This entire part is going to become 0. dc by dc, as we know, is going to become 1. Okay, so let's remove this, and now I'm going to rearrange this. One dot 0 multiplied by 2.0. Okay, let's remove this 1 dot. So I know that dg by dc is equal to this number. Let's remove this entire nonsense, and if I do the same thing for dg by dd, what will I get? What is the value of dg by de? 2.0. What is d by dd? E can be written as c plus d again. All of this is going to become 1.0. If I rearrange the terms, this is going to be the same thing. So I know the derivative of c and d, which is 1 multiplied by 2.0 and 1 multiplied by 2.0. What is 2.0? This is E dot gradient. And what is this 2.0? It is also E dot gradient. Correct. Or if I go back, look at this. dg by de, what is this? E dot gradient, right? That is exactly what we are writing. And what is this? F dot weight, E dot weight. Okay, these are the patterns that we are going to use for every addition and multiplication. In neural networks, we don't use subtraction or division among neuron communication. We are simply going to use addition or multiplication. Okay, so for that purpose, here I'm simply going to use only these two patterns. We are going to write a code for both of these patterns, so that right now we have calculated all these gradients manually, but once I write code for this, they are going to be generated automatically. So let me go ahead and write the code for this. So in my addition, I'll say output is equal to this entire stuff, and I'll return output. Let's put subtraction aside for now. And focus on multiplication. Even for multiplication, I'll be doing the same thing. So this is going to be output. Okay, I'm returning the output. Now we are going to use this particular rule. So what is this? Self dot gradient is something, and other dot gradient is something. What is this something? 1.0 multiplied by output dot grad. That's all right. So when I'm dealing with C and D, what am I taking the gradient? I'm taking the gradient of E. And if I go back to the diagram, C and D's output is E. So I'm taking the output's gradient. Don't worry guys, all of this will make sense once we keep going. And it's going to be the same formula over here as well. Okay, now when I put it here, the moment I do an addition, my gradients will be affected, right? I don't want that to happen. I want to modify these gradients when I want to, because if you look at the way we have modified these gradients, first we will modify the final output gradient as 1, and then we will go one step back and we will take calculate all the gradients in that layer, and then we will go one layer back again. So this is how we are going from layer to layer in terms of calculating all these gradients. From the last layer we need to come to the very first layer. So we want to change these gradients at the very end of calculations, at the very last step. Okay, so what I'll do is I'll take this code, I'll put it in a function called backprop. So whenever I call this function, both of these should be executed. How will I call this function? I'll create a new property to my output. I'm sorry, this is going to be output dot, what should I give it? Change grad. I'll call this as change grad as well. So whenever I call the change grad property, this function is going to be executed, and that is going to modify my weights. I'm sorry, that is going to modify my gradient. Let's copy the exact same thing, put it for multiplication, and these are the rules for multiplication. So this is going to be 1 multiplied by other dot weight, and this is going to be self dot weight. Okay, so for both of my numbers, I'm taking the weight of the opposite number. And similarly we are adding the change grads. Okay, everything looks good. Now instead of calculating all these gradients manually, what I can do is I can say e dot gradient is equal to 1.0, and then I can do what is this, g dot change grad. Oh, first I need to run this cell. Okay, so the new class has been initiated. Now let's calculate all these things, let's visualize it and make sure all the gradients are 0. Okay, there you go, they're all 0. Change grad for G, E, C, D. First we need to do it for G, and then to E, and then to F. Okay, but this is going to throw us an error, because what is change grad function? Change grad happens whenever we do either addition or multiplication. Unless you do addition or multiplication, if you are creating something from scratch, we don't have this function as a property, right? So let's create a fake function. Change grad is equal to, let's call it self dot blank. Now I'm going to create a new function called blank. What will this do? Nothing, absolutely nothing, because whenever I have root node, which are the A, B, C and F, these are the neurons that we can actually modify, right? So whenever I have these neurons, I shouldn't go back to a previous level. I shouldn't do anything. I don't want to go back and calculate any gradients or anything. I don't have anything to calculate, right? So the default property is going to be a blank function. Let me run that class, initiate this, go here. Okay, now after E and F we are going to call C and D, and then A and B. Oh, I'm sorry, I deleted it by accident. No worries, we got E, F, D, C, A, B. Change grad. Okay, all the gradients are 0 right now. So I've changed every single gradient. Now let's see what happens. Okay, so if you see here, all these gradients have been updated. So based on the rules that we give, the last one should become 1, and these both should exchange their weights into gradients, and whenever we are doing an addition, we will take the outputs gradient, and over here we are exchanging the weights into gradients, because this is a multiplication. Cool. So far all of this is working as expected. Now if I go back to the perceptron diagram, all of this is working exactly as expected. Now we need to add the step function. So what is the step function? This step function can also be called as an activation function. So there are so many different types of activation functions in machine learning. So activation function is basically going to shrink or reduce your output into a particular range. Let me let me show you what I'm talking about. Let me go to Wikipedia. This time let's go to Google Images. Activation functions. Okay, so these are the most famous activations functions actually. So we have all of the formulas written over here. Okay, let's look at tan hx. So whenever I pass any value to this, it's going to reduce the value to be confined to the range of -1 to +1. Okay, irrespective of what number I pass in, it's going to give me the confined value. So the higher the number, the more closer it's going to be towards +1. So if I have a value like 58,000 or 98 million, it's going to be very closer to 1 but not 1, very close to 1. It's going to be somewhere around like 0.99999 so on, but it's never going to reach 1 exactly, precisely. Similarly, if I have a very low number, a very large negative number, it's going to be very closer to -1. Okay, so all of these values, they are going to be in the range of -1 to +1, and at the edges they're going to sort of plateau out. The curve is going to become almost flat. That was tan h. Similarly, we have different kinds of activation functions based on the requirement, based on the application that we are trying to build, based on what the model is being built for. We use different types of activation functions. Most of the time we use ReLU activation function, and in some special cases we can go ahead and use the leaky ReLU activation function as well. For now, let's go ahead and implement tan h activation function. Okay, so let's go ahead and implement the tan h activation function. Here, where should I add it? Okay, at the very end, I'm going to define a new function called just tan h. It's going to take self, and to get the formula of tan h, I'm going to use Wikipedia again, or actually I think we have the formula right here. Do we? No. Okay, so let's go to hyperbolic functions. Okay, so we have tan h x. X is the input, so this is the formula that we are going to use today. E to the power of 2x minus 1 by e to the power of 2x plus 1. I'm going to use math library to write down this exact formula, and my x is going to be self dot weight. Okay, let's okay, so x is going to be self dot weight, and for t I'm going to use math. I need to import math. Okay, let's do that real quick. Import math, run that cell, come down. Okay, so math dot exponent of 2x minus 1, math dot exponent of 2x plus 1. This is going to give us the tan h value, and I'm going to create a neuron out of this t. And who are the parents of my tan h function? Self, nothing else. And what is the operation that I'm doing here? Tan h. Now let's return this output. Okay, this is good, but even for tan h we need to calculate the gradient, and to calculate the gradient, if I scroll down here, I think we should have formulas for that as well. Okay, there you go, derivatives. So the derivative of tan h is going to be 1 minus tan h square x. Okay, 1 minus tan h square x. What is tan hx? This. If I square it, I can simply use the same formula to calculate my derivative. So here I'm using the same change grad function. Now self dot grad is going to be 1 minus t square. What is t? Tan h square. And what is output dot grad? Since we are dealing with the finalmost layer, it's always going to be 1 multiplied by. So this output dot grad can be replaced with 1 dot 0. Okay, for now let's keep it as this. Let's remove the plus symbol here. So we are good to go with tan h function as well. Let me run this self, and over here h is equal to g dot tan h. H dot label is going to be capital H, and I'm going to visualize h, and here I'll add h dot grad, and we will have one more change grad function which is going to be h. Okay, everything looks good. Let me run this. Now using those class, we are going to create all these neuron objects. Let's visualize all the calculations. Okay, there you go. So all of these weights are as expected, and if you look at the tan h activation function, it has reduced 0.92 into 0.72, so it shrunk it down. Okay, and all the gradients are 0 right now. Let's go ahead and run this part. So every single gradient should have been modified. Now when I visualize this, there you go. Now you can see. So for tan h we are calculating the gradient and putting it as 1, and from there on we are doing back propagation to change the gradient of g, and then to ENF, CD, and then to AB. So from the very last node to the very first node in reverse order, we are calculating and modifying all of these gradients. Now this part was done manually by us. Let's go ahead and automate this. To automate all of this part, I'll write a function where for every node, for whatever node I give to this function, it's going to print all of its parents, subparents. Let's call it as print parents, and I'll pass a child to this function. So for this child, if the child has any parents, then I want to iteratively call this function for each parent. Okay, so for each parent I'm going to print all subparents. First let's print child dot label. I'm going to call this function and pass h neuron as my child. So let's see what happens when I run this. Okay, we got H G E D A B C F, H G E D A B. So I see what's happening here. Right now we are printing all of the subparents as subparents and then coming reverse into the child. Instead, if I put it here, we got AB, DC, EF, GH. Now I can simply reverse this order. To reverse it, I'll store all of these nodes in one array. These are called, that's called parents. So once my function is run, my parents will have all these numbers. Let's reverse the parents for I in parents. Okay, so for each parent I'm going to use I dot change grad. I'll call this function. Okay, I think that should do. And before I do this, the very first step is to modify the very last gradient to have the gradient of 1. Okay, now what I'm going to do is I'll simply run these calculations. Let's visualize all of this. All the gradients are 0 right now. Instead of running this particular cell, I'll directly run this. Oh, my bad. Parents dot append. String object. Oh, I'm sorry, I'm appending the label. Okay, there you go. Now when I run this, all the gradients are being modified perfectly. Okay, cool. Let's go ahead and take this, put it inside of our class. Here I'll create one more method called backprop. Inside of which I'm going to do all these calculations. So I'll take an empty array, my function, and instead of h, this is going to be self.grad, and the self.grad should become 1. Oh yeah, I need to pass self, I need to inherit everything from self, and instead of h, this is going to be self for I in reverse of parents, change grad of all of the parents. Okay, yeah, I think this looks good. Let me go ahead and run that. Backpropagation, let me copy this backprop. Now when I redo all these calculations and visualize, all the gradients are 0. Cool. I no longer need that cell either. I no longer need this cell either. I can go ahead and simply delete them and then do h dot backprop. When I run this, automatically all of my gradients have been modified as expected. Okay, cool. Okay, what did we cover so far? So far we have created neurons, and these neurons are able to communicate with each other, and we are also passing all these neurons through an activation function, and once everything is done, we can do back propagation and we can calculate all the gradients from the very last neuron till the very first neuron, all the layers. Okay. Now, right now, all of this is working as expected. Okay, so right now all of this is working as expected. Now we are going to start building actual neural networks. So to do that, first, if I go back to perceptron diagram, okay, so if you look at what we are doing here, I don't think this is the perfect one to explain. Let's take this one into consideration. So x1, x2, x3, so on, these are going to be my inputs. W1, W2, W3, these are all going to be my weights, and I'll take one more weight here which is going to be called as bias. Okay, so every perceptron will have a small amount of bias. I'll multiply all of my inputs with my weights. I'll take my bias, I'll do a summation of all of them, and whatever result I get out of it, I'll be passing that through my activation function. Okay, so we need to construct this exact same structure with our neuron class. Okay, so instead of using these sort of objects, I'm going to recreate this entire diagram with Python code. Let's see how that goes. Okay, in a new cell, I'm going to paste this existing code. Okay, here I've got x1 and x2. These are going to be my inputs. Similarly, I've got w1 and w2. These are going to be my weights. And also I've got a small amount of bias here stored in B. And now first step is going to be x1 multiplied by w1, x2 multiplied by w2. Okay, so I'm multiplying the first input with first weight, second input with second weight. Once I do the multiplication, I'll give them proper labels again, and after that I'll do a summation. I'll add all of these multiplication values. So whatever I've multiplied so far, I'll just add them up, and for whatever result I get there, I'll add the small amount of bias, just like how we see here. I'll take all of my inputs, all of my weights, I will multiply them, and whatever result I get, I'll add bias to that. That is going to be my output, and for that output I'll call the tanh activation function. This is going to be the final most output. Out. I'm representing that with O. Cool. Let's run this, and let's do O dot back propagation. So right now all of the gradients should have been updated, right? Now let's use draw dot function and take a look at how O looks like. There you go. I've got my x1, w1, x2, w2. All of these weights have been modified with the help of back propagation. So multiplication of both of these is giving me x1, w1, x2, w2. Addition of both of them has given me this result, for which I'm adding my bias, and for that result I'm just taking the tanh. So everything is looking pretty good so far. So whatever we have created just now is one perceptron. So everything inside of this diagram is one perceptron, and as I've told you in the very beginning, each perceptron contains all those different aspects, whatever we have built so far. But now we need to go one level beyond this. Now we need to go ahead and create layers. Okay, so every layer should have n number of perceptrons, and all these layers should be able to communicate with each other. So that is when we build the actual neural network. So far we have been building just neurons and perceptrons. Now let's connect all of them together. Okay, so this is where we stopped. This is my entire perceptron. I'm taking all of my inputs, all of my weights, multiplying them, adding them up, adding the bias and the tangent activation function. Cool. So this perceptron is ready. Now let's go ahead and build the actual neural network itself. So from this diagram we can see that each perceptron, let's go back here actually. Okay, so here we can see that from each perceptron we have n number of weights. So we can create as many weights as we want, but we need to make sure that the number matches with how many inputs we are sending to the model. Okay, so first let's take input data. That's going to be the most important one. So my input data is going to be let me take some random numbers here. To 0.9. Okay, so here I'm taking 4 input values: x1, x2, x3 and x4. Now let's go ahead and create a perceptron. To create a perceptron, I'm using one more class here. Let's name it perceptron, and whenever I'm creating this, I need to pass number of weights. Okay, so whenever I'm creating the perceptron, I need to make sure that I'm passing how many number of weights do I want to initialize in this perceptron. In this example, we can see that we have used 2 weights, W1 and W2. Similarly, here we are going to use the number whatever we are sending to this perceptron. To do that, we can use list comprehension. So this is going to be x for x in range of number of weights, and I want this x to be a neuron. I'll call this self dot weights plural. Okay, now what is going to happen? Well, self dot weights is going to be a list of neurons. From this perceptron diagram, we can see W1, W2, so on up to Wn. So all these W's will be stored inside of a list. So what is X here? X is the range value. So if I give, let's create an object for this perceptron. I'm going to call it model. So right now in the entire neural network model, we have only perceptrons already. So let's create a perceptron object with 4 perceptrons. Okay, we are going with the exact same diagram that we see here. Let's go with this one. Okay, it's the same thing. Okay, let's go back. Okay, let's go with this one. So we got 4 weights here. Three of them are being used for my inputs. One of them is being used for bias. Let's use 3, and let me remove one of these inputs. Okay, so we got 3 inputs, and for that we are generating 3 correspondent weights. I'll quickly run this, and of course we get an error. Float object cannot be interpreted as an integer. Okay, I'm sorry, my bad. Okay, there you go. Now in a new cell, I'll simply do model dot weights. So there you go. In an array, I'm storing all these neurons. But if you see here, X is a range. So that is why we are getting data as 0, 1, 2. So if I pass 30 here, it's going to be 0, 1, 2, 3, 4, 5, 6, 7 until 30. To get rid of that, I'm going to use a random number. Okay, this is going to be a random number. First, let's import random library. And if you don't know about this, random library has a method called uniform, wherein it's going to take a range and it's going to give you a value within that range in a uniform way. So there aren't going to be any bias towards, or there isn't going to be any scenario where you'll end up with 90% positive values and 10% negative values. Okay, so the distribution of these values is always going to be uniform. So even if I run this particular cell 100 times, whatever values I get, they are always going to be uniformly distributed. Right now we got 0.81 minus 0.76, 0.67, 0.06. Okay, that's how this works. Let me take this random uniform and I'll create a neuron with this random number. I'm going to put you right here. Okay, this looks ready. Now the bias. And this bias is also going to be a neuron of random weight. And we just want only one neuron. Okay, this looks good. So far we have created all these weights and the bias term as well. Now we need to multiply the inputs with all of my weights and then do a summation and then add my bias. Let's quickly do that. So here I'm going to utilize call function. So the call function is a built-in method where I can pass any particular value to this. Let's call this as input, and I can utilize that function. And I can utilize that argument okay, here I'm using an f string to simply do a print. Okay, and when I create my model, I'm going to say model of input data. So simply whenever I call my object is going to go and call this particular function. So whatever arguments that I pass while calling it will go here. Okay, let's run both of them. And as you can see, input data is this one. Okay, now what we should be doing is, we have got 3 weights and we got 3 inputs. We need to group them. Okay, so the first weight and the second weight, the first weight and the first input, second weight and second input, third weight and third input, these 3 should be grouped together. To do this kind of grouping, we are going to use the zip method present in Python. If you don't know what zip does, well, basically if you have 1, 2, 3 and 4 and b is equal to 9, 10, 11, 12. I've got 4 values in A, 4 values in B. For group in zip of A comma B, let's print the group. There you go, this is what happens. So 1 and 9 will be grouped together, 2 and 10 will be grouped, 3 and 11, 4 and 12. Okay, so we want to do this kind of grouping with our inputs and weights. So in the call function, I'll say for group in zip of self.weights, and inputs. Okay, so we are going to zip both of them. This is going to be input singular. Let me just print group first. Okay, so there you go, the grouping is being done properly. So my neuron is being grouped with my input. So instead of group, this is going to be W and X. Let's print W comma X. I'll run both of these cells, and there you go, we got our weight and X, the input. Now I'll simply multiply them. When I multiply, the output is going to be 1 neuron for each weight. Now what we need to do is, we have to store this multiplication value somewhere. Let me store all of this in let's call it WIXI, since we are multiplying W's and X's. This is going to be an empty list. WIXI dot append of WX. Let me print WIXI. Okay, so when I run this, the multiplicated values are being appended to my WIXI. So this multiplication has been taken care of. Now we need to do a summation. So if I do a sum of WIXI, what do we get? All of those neurons have been added to give me 1 neuron. So even the summation has been taken care of. Now I need to add the bias term here. So let's go ahead and store this in result is equal to this entire part, whatever we have been printing so far. For this, I'm going to add my bias. Okay, remember guys, bias is the neuron that we have created at the very beginning itself. So this is going to be a random neuron. Okay, the bias has been taken care of. Now the activation function, result dot tan h, and I'll store this inside of output. Let's go ahead and print this out. There you go. So every time I create one perceptron, it's going to do it's going to create all of the weights. It will take my input data, multiply it, add it, activate it, all those things will be done. And every time I do that, I get a new data for my neuron. Cool. So as of now, we have successfully created one neuron. The next step is going to be to build one layer containing multiple neurons. Let's go ahead and do that. To build that, what we are simply going to do is, I'll store every single perceptron in an array. So this is going to be one long array, and let's build this layer. Okay, so we got 4 bubbles here, 1, 2, 3 and 4. Okay, so all these 4 are going to be perceptrons. So I'll say perceptron for x in range of 4. For I in range of 4. Okay. Now all of this will be stored in one long array. Okay, so there you go. My array right now has 4 perceptrons. I'm not passing my input data to these perceptrons, okay? And that is the reason why you're seeing all of this nonsense. Now let's go ahead and utilize one more class to do this exact same thing. I will call this as layer singular, okay? Layer, not layers. Because right now we are creating all of the code to create only one layer. Later on we will see how we can create multiple layers. Okay, so what is this layer? This will take self and it's going to take number of perceptrons. This is self, not elf. 2 underscores. Cool. So far good. Let me go ahead and take this and put it here. I'll call this self dot layer is equal to. Okay. Now perceptron of 3. What is 3 here? 3 is the number of weights that we are creating. How do I know how many weights do I need to create? Well, based on the number of data points we have inside of our input data, we create these weights, right? So which means I need to take one more parameter into consideration, which is number of weights. Okay, I'm going to use this here. So every time I create a perceptron, I'll use this number of weights. And how many perceptrons do I actually want? That will be stored here. Cool. Now let's go ahead and create layer. And this layer will take how many number of weights? Well, it's going to take 3 weights and I want 4 perceptrons. Just like how you see here. 3 weights, 4 perceptrons. Okay, number of weights, number of perceptrons. Now let me run this. Let's not do this part for now. I'll comment it quickly. I'll run this. Now I'm creating a model, and for this model I'll do model dot layer. There you go. So right now I'm able to create 4 different perceptrons for one layer. Now I need to multiply all of my inputs to these perceptrons. Here again I'm going to use the same call function. Take all the properties from self, and now I'll use the exact same variable here, input, and for each perceptron in my layer, I'll simply do P of input. So every time I do that, my perceptron will take all of the weights, multiply, add and everything, and then the activation function, and then it will give me one output. Let's call this as output, and I'll be storing all of these outputs in one array. What should I call this name? Damn, it's always a very difficult thing to name every single variable. Let's call it self dot perceptrons is equal to an empty array. So I'll take all the self.perceptrons dot append output. So whatever output I'm getting here will be appended to self.perceptrons. Let's print self.perceptrons. Now I'm going to pass my input data. Oh, perceptrons. I'm sorry. Let me delete this. Okay. Am I printing this? Oh, there you go. Let's not print this part. I should be returning self.output. So every time I'm doing the calling, it's not returning anything. And that's the reason why we are seeing all these nulls here. Okay, there you go. So I've got 4 different outputs. So which means this layer is giving me 4 different outputs. Which are the outputs of each perceptron. Okay. Now we need to go ahead and create multiple layers, and that's where we enter into something called as multi-layer perceptron. So when you look at neural networks, the most basic architecture is going to be this one, what you see on screen here. Okay. Now what happens instead of the most basic neural network is you'll have an input data, some very few hidden layers and an output layer, and all of these hidden layers are filled with perceptrons, nothing else. There aren't going to be any complicated models here. So we are not dealing with any convolutional network, we are not dealing with any LSTM models, any of those kind of layers. Okay, so this is going to be very basic layer, and that's the reason why we call basic neural networks as multi-layer perceptrons, since it has multiple layers. That's it. Now let's go ahead and create multiple layers. I'll create one more function. Oh, by the way, I should be returning this. Okay, I'll create a new class. I'll call this as MLP, multi-layer perceptron. And whenever I'm creating this multi-layer perceptron, what I should be doing is I'll pass my inputs, which is going to be this part, and I'll say how many number of perceptrons do I want and how many number of layers do I want. First thing is input, and then comes number of layers, and then we have perceptrons for each layer. So these are going to be the 3 things that we need to create an MLP. Inputs, how many layers do you want to create, and within each layer, how many perceptrons do you want to create. Okay, so keep in mind, whenever we are creating all these layers, every layer may or may not have same number of perceptron. Sometimes we might find networks with huge number of perceptrons. Sometimes we might find layers with very less number of perceptrons. So to handle this kind of situation, what I'm going to do here is I'll simply take an array and let's say 4 comma 3 comma 4 comma 3 comma 2. Okay, so when I do this, my number of layers is going to be length of this array. Okay, so the number of layers is going to be the length of this array, and each number indicates how many perceptrons do I want in that respective layer. Okay, so which means in the very first layer I want to have 4 perceptrons, in the next layer I want only 3 perceptrons, and in the next layer I want only 4, and then in the next 3, next 2. Okay, so which means this is going to be the output layer. Okay, cool. Let's see how we can utilize this. Now here I'm going to build this exact same architecture. Okay, so I'll take 3 inputs, 4, 4, 4, 1. So I'll take 3 inputs, 4, 4, 4 and 1. Okay, so 3 are going to be the input perceptrons, 4, 4, 4, and finally the output layer is going to be 1 neuron, 1 perceptron, I'm sorry. Now instead of calling this MLP, instead of calling it layers, let's call it MLP. And here what I'm going to do is, if you look at the neural network, every time we create layer, we need to send 2 things. How many weights do you want, and what are going to be the number of perceptrons in that layer. So if you look at the very first layer, what is the number of weights that we need to create? It's the number of inputs that we are receiving to this layer. Okay, so if this green layer has 4 perceptrons, okay, so this green layer, look at the layer before it, it's the yellow layer, and we got 3 perceptrons here, which means every perceptron in this layer should receive 3 weights. It should contain 3 weights. So the number of weights depends on previous layer outputs. Look at the second hidden layer. How many weights are we creating here? Every perceptron has 4 weights. That is because the previous layer has 4 outputs, right? This is going to be the output. So what I'll do is I'll quickly just write one small piece of code. So let me replace all of this with this code. Let's delete this. Okay, so now my MLP takes 2 parameters. One is number of input neurons, and the second one is going to be number of layers. Okay, and when I do this, here I'm doing some simple magic, and let's print for I in self dot layer list, print I. That's right, we can't call it yet. Okay, there you go. So inside of my layers list, I'm creating these groups. So initially I'm sending 3 inputs, right, which is this one. So whenever I'm creating a layer, I'll say number of weights are going to be 3, and how many perceptrons do I want in this layer? I want 4 perceptrons. Look at this, 3 inputs, 3 number of weights, 4 perceptrons. And in the next layer I've got 4 by 4, 4 weights, 4 perceptrons, 4 by 4 again, 4 weights, 4 perceptrons, and finally we got 4 by 1, 4 weights, 1 perceptron. Cool. With this, let's go ahead and create our layers. So I'm going to say layer of self.layers is going to be a list, and for this I will say dot append all of this. So every time I create a layer, I'll be appending that to my self.layers. And now let's go ahead and use the call function. Inside of the calls, I'll send input. For each layer, I'll send my input. Okay, so every time I send my input, it's going to return me this part, right? Self.perceptrons. This will become my new X. This will become my new input. So initially, okay, so I've got 3, 4. So in the very first run, I've got 3 inputs, these 3 green bubbles. And these 3 are going to communicate with the first hidden layer. So which is going to be this part. My layer is going to communicate with the input. Then whatever I get from that communication will become the input for next layer. So that's why whatever I get from there, I'll store it in input, and in the next layer, whenever I'm going to the next iteration, I'll use the previous output as present input. I'll use the previous output as present input. Okay, so H1's output is going to become the input of H2. Once I do all of that, at the very end, I'll receive one output, right? This is going to be the, let's not call it input, let's call it X actually. So let's return X. So whatever output I'm receiving at the very last network, very last perceptron, very last layer is going to become my final output. Okay, everything looks good. Now let's pass the input data. Let me run this cell. Let me run this cell. There you go. Now we got one neuron as the output. Notice here, this is inside of a list. That is because every time we do this communication, it's returning everything in the form of a list. This list. So I'll quickly just modify this x of 0. So I want to return the very first element if length of x is 1. Else just return me direct x, the entire thing. Let's run both of them. There you go. Now it's returning me only one output. Cool. So I think with this we have created the forward propagation. Now we need to do the back propagation to all of this. So before we go there, I'm going to use one different value for my input data. Okay, so let me go ahead and replace all of this with this part. So here what I'm doing is, in my X data, I'm taking 4 separate data points. Okay, so whenever you're dealing with any kind of machine learning problem, you'll have a data set, and within that data set, you'll have multiple rows. Right now, I've got 4 rows. And for each of those rows, I've got my Y, my target variable. Okay, I've got my X and Y ready. Now, whenever I'm creating my MLP, what is going to be the number of input neurons? That is going to be the length of X data. So how many number of data points do I have will be the number of input neurons. And this is the number of layers. Okay, so I want 4, 4, 4, and then finally 1. So let's run this and this. Now in a new cell, I'll take my model and now I'll send my X data. But notice here, this is I've got four of these points in an array, so I can't give it directly. So instead, what I'll do is, for X in X data, I'll do model of X. Okay. Actually, instead of model, can I just say train? So model.train X. So every time I do the training, the output layer is going to give me one neuron, and I'll store that in ypred because that is the prediction of my model. Okay. Now let's print ypred and print ytest. So I've got 4 different outputs and 4 different actual values. So these are predictions and these are test values. These are the ground truth. Okay, now somehow we need to calculate how good is our model's performance. Based on that, we are going to do the backpropagation. So I hope you're familiar with the concept of loss function. So essentially what we're going to do is, if I know that the very first output should be 1, and if my data, if my model gave me the output as minus 0.064, then I can basically calculate how different is the prediction compared to the ground truth. How far away are they? Okay, that can be calculated with the help of loss function. There are so many different types of loss function depending upon the use case, depending upon what you are trying to build. You can go ahead and choose the loss function. Right now I'm going to use the most simplest loss function, so which is going to be bigger value minus smaller value. That's it, very simple one. So from both of these I'll take this as the big value and this as the small value, and then I'll do a difference. That's it. But sometimes if you look at this example here, 1 is obviously greater than whatever prediction that I got here. So 1 is greater than minus 0.06, right? So if I take this neuron as the bigger value and 1 as the smaller value, the result, whatever I get, the difference is going to be a negative number. But we don't want that. We want that to be a positive number. So for that reason, what we do is I'll take this entire thing and I'll square it. Okay, so once I do that, I'll be converting that negative number into a positive number. So irrespective of which is bigger, which is small, my output is always going to be a positive number. And I'll repeat this process for every group. Okay, and to do this, again, I'm going to utilize the zip function. So I'll do a zip with ypred and ytest, and for each group I'm going to calculate this loss function. So let's go ahead and write a code for that. Okay, so this is a very simple list comprehension. So I'm doing a zip on ytest and ypred, and in every group I'll receive my ground truth and my output. I'll take them, I'll calculate the difference, then I'll do the square. So whatever result I get here, I'll do a sum of all those results. Okay, so once I do the sum, all of this result can be stored inside of a variable called loss. So this is going to be the actual loss of my entire neural network. How good or how bad is it can be calculated at this point. Once I calculate the loss, I'll simply do loss dot what was this, back propagation, what was the name, there you go, back prop. Okay, so once I calculate the loss, I'm going to use loss dot back prop. Before I do that, let's do a draw dot and visualize how loss looks like. Okay, cool, everything looks good. Now let's run all of these cells. I'll create all those classes. I'll take my x data, y data. I'll create my model here. And now I'll do the training part. After that, I'll calculate my loss. Cool. Now let's go ahead and visualize how the entire network looks like. So this is going to be a very big network, very complicated network actually. But we know what is happening inside. It just looks very big and complicated, that's it. Okay, right off the back, you can see how big this picture is. So if I go somewhere into the middle, there you go. You can see how complicated all of these calculations are going to be. So every single one of these calculations is being done automatically. You don't have to worry about anything going wrong. Just look at those number of communication between nodes. And if I scroll all the way back, actually Okay, so when I expand this entire thing, I might have to zoom out a bit more. Okay, here you can see how complicated all of this has become. It looks phenomenally beautiful. And as we reach till the end, we got only one thing as our loss. Okay. Now if I go back to this diagram, every single gradient is set to be 0.0. Now simply when I do loss.backprop, all those gradients are filled automatically, every single one of them. And look at the time consumption, it took just 0.1 second. Let me scroll down a bit. Now let's draw this. Okay, there you go. So every single gradient has been calculated. Now what does this gradient say? This gradient tells us how much is this particular node, or how much is this particular neuron affecting my final output. What is the final output? My loss. Okay, so which means indirectly I can rephrase it and say that the gradient here tells me what is the effect of this particular neuron on the model's accuracy. So if I modify this neuron by a small amount, what is going to happen to my accuracy? How good is my model going to perform if I modify this neuron? Okay, so that is calculated by dy by dx, which is the gradient. Now we are going to use this exact same gradient to modify all of our weights. So the way model training works is we have epochs. So every epoch is going to be an iteration. So let's say we have 10 epochs. In the very first epoch, we will do forward propagation, and then we will do backward propagation, and we will move on to the next epoch. Even in the second epoch, forward, backward. Third epoch, forward, backward. So what is going to happen in forward propagation is all of my weights are going to be created. Initially, in the very first epoch, I'll randomly initialize all of these weights. Since we have the random.uniform function, we are going to use the random.uniform and create all these weights. And based on these weights, we are going to do the predictions and calculate the loss. Based on this loss, I'll do back propagation, loss.backprop. So all of my gradients are going to be filled with some values. Using these gradients, I'm going to modify my weights. So every single weight, I'll either add some amount to it, I'll decrease some amount to it, I'll increase or decrease those weights. And now when I do these addition and subtraction to my weight, I've got a complete set of new weights, right? Until now, first epoch is done. With the help of these new weights, I'm going to do forward propagation once again. So which means I'll take my input data, I'll multiply it with my weights, I'll do all the multiplications, adding the bias, activation functions, I'll do all of these things. Then I'll do y-pred, I'll take my y-test and y-pred, I'll calculate the loss. This entire thing is forward propagation, right? Once I do this, I'll do loss.backprop once again. So now, in the second epoch, whatever new weights I had, I'll get completely new gradients. Now I know how much is a particular neuron with an updated weight, okay? Now I know how much is this particular neuron affecting the entire neural network again. In the next epoch, I'll modify the weight of this neuron with forward propagation and backward propagation, and then I'll calculate the loss. Now I'll do loss dot backprop, I'll get the backpropagation, I'll get the gradient. Similarly, I'm going to keep on repeating this process until my loss becomes zero. Not zero per se, but until my loss goes very down. So if my loss is somewhere around 3% or 2%, which means my model is able to predict correct results 97% of the time. That is a very good model. So until I reach such low value for my loss, I'm going to keep on repeating these epochs. I'm going to keep on repeating these forward and back propagations. Okay, so what all nonsense I've just said now, let's go ahead and codify all of that. Let me delete this, it's very hard to scroll. Okay, so whenever I do this, I want to calculate the loss. Okay, right now the loss is at 3.9%. So I'll do loss dot back propagation. So all the gradients have been filled. Now we need to update all of the existing weights with new weights. How do we do that? To do that, first I need to fetch every single weight that is present in my model. So every single neuron's weight should be stored in one long array. So I'll go back to my initial class, and when I go to perceptron, here I'm going to create one more new method called getWeights. So this will take self, every single self parameter, and I'll simply return my self.weights plus self.bias. If I go back to perceptron, these are essentially what we are creating, right? These are essentially what make our model. These weights are the reason behind these weights control the accuracy of the model, right? So we got all of our weights and one bias. I'm returning all of them here, all of my weights and one bias. I'm putting everything inside of a list. So I'm putting everything inside of a list and I'm returning it. Cool. Now I need to call this function for every single perceptron. How do I do that? Well, I'll create one more method here called getWeights. And I'll use the same code and I'll call this layer weights. So for each perceptron, I'll do perceptron dot getWeights. These are going to be my perceptrons weights. So I'll take all of the perceptron weights and I'll combine them together instead of layer weights, and I'm going to return them. So with this piece of code, for every layer I'll go perceptron by perceptron, I'll calculate and I'll collect all the weights, I'll store them together. So by the end of all these collections, I'll have one long array of all the weights that are present in that particular layer. And now simply let's repeat this process for every single layer. Copy, paste. Okay, I think this is a bit more optimal. Now instead of get weights, I can use okay, I don't think I can use any of those things. Okay. Here I'm going to use for each layer all weights. Okay, so for each layer I'll say layer dot get weights. And whatever result I get should be stored inside of my all weights. And I'll simply return all weights. Okay. Everything looks good. Now let's go ahead and do model dot get weights. Okay, everything looks good. Now let's go ahead and run everything. Let's see what happens. Unsupported operation between distinct float. Extend. There you go. So when I say model dot get weights, every single weight is being stored inside of my model. Let's see the length of this array. 65. Good. So for such a small network, we have 65 different weights. So these are going to be the number of parameters. Okay. So right now I can confidently say that my entire neural network contains 65 parameters. So whenever you do model.summary on any TensorFlow model or any Keras model or any PyTorch model, you will get a detailed summary of the model, and at the very end you can see XYZ parameters. So it's going to be somewhere around like 20,000 parameters, 55,000 parameters, 1 million parameter, 12 million parameters. So ChatGPT 3 was trained on 10 million parameters, 20 million parameters. So which means that particular model that they've built contains 10 million weights. Okay, so that's how big models can get whenever you are increasing the number of layers and increasing the number of perceptrons. So for each of these weights, what I'm going to do is let's call it weight. or let's call it W itself. W. So W dot weight plus is equal to small step size multiplied by W dot grad. Okay, so this is how we modify the weight of every single perceptron. So I'll take the weight. For that I'll add a small amount of small shift to it. Okay, so this is called as a step size. So the weight is going to be increased by a small step size, and then I'll multiply it by whatever gradient I've got. This is how we modify the weight. So eventually the gradients are going to decide how much exactly should we modify the weight. So if a particular weight has a very high gradient value, then the weight is going to be modified by a huge number. So once I update all, okay, so here I'm updating all of my weights. Until now, the entire forward propagation is done. Now I need to do backward propagation. Oh, I'm sorry. Okay, so until now, forward propagation and backward propagation are completely done. So when I do loss.backprop, gradients have been calculated, and with the help of those gradients I'm updating my weights. Both of this comes into backward propagation. And the training part comes into forward propagation. Okay, this looks good. Let me clear all of my outputs, and this is where I'm creating my model. Okay, everything looks neat here. So I've got my data in this cell, and I'm creating my model over here. This is forward propagation, this is backward propagation. Backward propagation. Cool. But all of this is for one epoch. So let's create the data, model, forward, and my loss is 4.42. Now I'll do back propagation. So once I do back propagation, all of my weights have been updated. With these new weights, I want to calculate my new gradients, right, in the next epoch. But when I'm doing that, I already have an existing value in neuron's gradient. So if I have neuron called A dot grad is not empty. There is a particular value in there already. I need to change that value back to 0. So which means this new weight, we are not sure how exactly is that new weight impacting the final output, correct? So that's why whenever we are changing the weight, we need to bring the grad value back to 0. So I'll create the model. So in the first epoch, forward propagation gave me a loss of 4.6. Then I'll do backward propagation. Now when I do forward propagation again, the loss has been changed. Backward again, forward again. Okay, so a smaller step size here is Okay, so now the loss has been reduced to 4.34. So similarly, for every single epoch, the loss is going to come down. I'll take both forward and backward and I'll put them in a for loop. So let's go ahead and write a for loop here. Okay, let's write a for loop for epoch in range of 20. I'll do forward propagation first, and then I'll do backward propagation. And for every epoch I want to see the epoch number and loss. Let's use f string. So loss dot weight should work. Cool. And similarly, once I do this, I'll take all the weights and all of the gradients should become 0. Okay. Okay, there you go. Here you can see. So initially the loss was at 5.9%, and slowly the loss, the concept of stochastic gradient descent comes into place here, but eventually the loss came down all the way up to 3.7% for 20 epochs. So we can go ahead and repeat this for n number of epochs, and at the very end you have got your model ready. So you can go ahead and use this model for any of your regression tasks. So this is basically how neural networks are built from scratch. I hope you enjoyed this tutorial, but most importantly I hope you understood how exactly forward and backward propagation work. So these are the most fundamental and very important concepts which are running all neural networks, all deep learning models. Okay, so I hope you understood them very well. I hope you enjoyed this video, and if you made it this far into this video, then I sincerely thank you for watching all of this, and please do like, share and subscribe. Thank you.